Hey y'all, so the first thing we're going to learn today is how to find the x and y intercepts of a graph of parametric equations. So I'll use this example to kind of showcase how to do that. So when you have x and y intercepts, what those points represent, and I'm just going to sketch some sort of random curve on here. This is not going to be related to these equations. But let's say I had some curve that does this, right? My x-intercepts are going to be all the coordinates where the graph crosses the x-axis. And for all of those coordinates, the y value is the same, and it's 0. Like this might be something like -5, 0, -1, 0, 3, 0. But in all cases, no matter what the x-intercept is, the y value is 0. Similarly, when you try to find y-intercepts, those are the points that are going to lie along the y-axis, that vertical axis, where x equals 0. So to sum that up, to find the x-intercept, you're going to set the y equation equal to 0. And to find the y-intercept, you're going to set the x equation equal to 0. So I'll break that down as we go through it. Let's go ahead and get into it. So as I was saying, the x-intercepts. And there may be more than one, so we'll find out once we solve it. But the way that you find them is you are going to set y equals to 0, right? Because all the coordinates that lie on that x-axis, every single one of them has their y-coordinate 0. So if we can find the time when the y-coordinate is 0, we can use that time, plug that in here to find the x-coordinate. And that's going to be our overall strategy here for both the x and the y-intercepts. Set the other equation equal to 0, solve for t, and then plug that t back into the other equation. So let's solve the y equation for t. We get 3t squared plus 5t minus 12 equals 0. What we have here is a quadratic, and I'm going to solve this quadratic by factoring, and specifically I'm going to use the factoring by grouping technique. So I need to come up with two values whose product is -36, and that's coming from the product of the constant and the leading coefficient. And so I'm going to put a little multiplication symbol up here just to remind me. Two numbers whose product is -36 and whose sum is 5. Okay, so we're looking for two numbers that multiply to give me -36, and those same two numbers need to add up to 5, which is this b term right here. So yeah, this is a times c, and this is b. Just as a little refresher on how to do this grouping technique. So those two kind of special numbers are going to dictate how I break up this middle term. Okay, in this, we're not going to go over all the little details on factoring by grouping, but we'll go over kind of the gist of it here. So I've got 3t squared and -12. Those two terms are going to remain the same. I'm just looking for a way to split this up so that I can use the grouping technique. And there are infinitely many ways we can add up two terms to equal 5t. Like we could do 1t plus 4t or 2t plus 3t. But there's only one specific combination that will work for this technique, and we'll find out the coefficients of those linear terms by doing this little game, playing this little game, where we try to find two numbers that multiply to give me -36 and add up to 9. So those two numbers, those two sort of special numbers in this case are going to be -4 and 9. Because -4 times 9 is -36, and -4 plus 9 is 5. So the correct way to split up that middle term is going to be -4t plus 9t. From there, and this is where the technique gets its name of factoring by grouping from, is we are going to factor out, or I'm sorry, we're going to group the first two terms and the last two terms and factor out the GCF out of each group. So out of the first group, we factor out a t, and we're left with 3t minus 4. And in the second group, we're going to factor out a 3. As you're doing this factoring by grouping technique, this is where you sort of want to throw up the stop sign, take a moment, and check to make sure these two factors are identical. If they're not, either you did something wrong or the thing's just not factorable. So if you get them to be the same, that's good. That means we're doing this correctly, and that will be one of your factors, and the other factor will be the number that you're the number or the variable that you're multiplying by. So in other words, this would be t plus 3. So from here, we're going to use the zero product property to solve this equation. We're going to set each each factor equal to 0, and we're going to solve, because if two things multiply to equal 0, then one of those two things has got to be 0. And we get t equals 4/3, or t equals -3. Okay. Now, normally what we would do is we would plug both of these t's into the x equation to find the x-intercept. However, make a quick note that there's a domain restriction on this one. So if there's no domain restriction, then you can just throw them both in and you're going to get multiple x-intercepts. But because this specifies that t's got to be less than 0, we're going to eliminate this as a potential time where we have an x-intercept, because that's outside of that domain. So the only one we really need to test here is t equals 3. Okay, so I'm going to substitute t equals 3 into this top equation so that I can solve for x. So I've got x equals this -3 cubed plus 1. Okay, -3 cubed is going to be -27, plus 1 is -26. So what we get is an x-intercept at -26, 0. Okay? That's an x-intercept. So that's where this graph will be crossing the x-axis. And we know when that's going to happen. We actually knew when it was going to happen before we knew where it was going to happen. It happens at it happens when t equals -3. So that's the x-intercept. And let's see if we have any y-intercepts. To solve for the y-intercepts, you're going to do a very similar process. Instead of setting the y equation equal to 0, you're going to set the x equation equal to 0. So I'll have t cubed plus 1 equals 0. Subtract 1 from both sides. Take the cube root of both sides. And the cube root of -1 is just -1. So that's pretty easy. A little bit easier than this other one. We don't have to do any factoring or anything too tedious on that guy. So we know the time, we know when the y-intercept occurs, but let's figure out where the y-intercept occurs. We know the y-intercept occurs when x is 0, but we also need to know what's the y. So the y is 3 times -1 squared plus 5 times -1 minus 12. Something you could throw in your calculator. What do we got here? 3 times 1 minus 5 would be -2, minus 12 is -14. So I have a y-intercept at 0, -14, and an x-intercept at -26. So this is how you find the x and y-intercepts of any set of parametric equations. Just to recap here, to find the x-intercept, you set y equal to 0, solve for t, plug that into the x equation. To solve for the y-intercept, you're going to set the x equation equal to 0, solve for t, and plug that into y. So a similar process, whether you're finding the x or y-intercept, it all just depends on which one you're looking for, and in that case, you set the other variable equal to 0. So let's talk about something slightly different, okay? What I want to ask you is, what is the difference between an intersection and a collision? So if you have sets of parametric equations that describe the path of two different objects, how would we differentiate between answering the question, did their paths cross or did their paths intersect, and did they actually collide? The piece of information that we would need to know to be able to answer that would be, what time did they reach that intersection point at? Let me give you a little example here. Take a look at this map. Let's say you and I both get hungry for lunch, but not at the same time. So let's assume I have A lunch and you have B lunch. So at when A lunch comes around, I'm going to leave Lake Travis High School. I'm going to come out the back here, and I'm going to drive to, let's say, P. Terry's, okay? And I drive here. I go through the drive-through, I get my burger, and I come back. A little bit later in the day, B lunch rolls around, and you're like, okay, well, I'm kind of hungry too. I'm going to go to P. Terry's and go grab myself a burger. So maybe you go out the front, you go down Cavalier Drive, but you're still going to go to the same P. Terry's. You're going to wait in that same drive-through line. You're going to get your burger, and you're going to come back and eat your lunch back at school. So we both drove to P. Terry's for a burger. We waited in line at the drive-through. We picked up our food, and we went home. We would say that our positions intersected at the drive-through. We were both at the same place at some time. However, since we were there at different times, we would say that our two paths did not collide. So let me break that down. Put simply, two graphs will have an intersection at a coordinate, in this case P. Terry's, we'll call it xy, if that ordered pair satisfies both functions. But we can go one step further and say that that intersection is also a collision if that ordered pair satisfies both functions at the same time. In other words, if the xy coordinate works for both sets of parametric equations, when t is the same, then we say we have a collision. Okay, we would run into each other if we were in the same position at the same time. Let's take a look at an example of how we would find points of collision or intersections, if they exist, and we'll be able to find through the solving process whether or not there even are any. So I'm going to show you one way how to do this that I think might be a little bit longer than a different way, and I'll show you the shorter way too, but I kind of want to just talk through this and kind of solve it how you might think about it. So first, let's see if we have any intersection points, because if we don't have any intersection points, we obviously can't have any collisions, because if they never touch the same location, then they can't touch the same location at the same time, right? So first we'll decide, hey, are they ever in the same place? And then we'll try to figure out, well, was it at the same time? So first, let's find the intersection points. To do that, I'm going to write both equations in rectangular form. So this is something we did last class, where we tried to write y in terms of x. And the way to do that is essentially solve your x equation for t. So like if if x is t minus 2, then that means t is x plus 2. Similarly, over on object 2, if x is 1 minus t, then t is 1 minus x. So we can take that expression, right, this x minus 2 expression, let me try a different color there, and substitute it into t for the y equation. When I do that, I get y equals x plus 2 minus 1 for this one, and I get y equals 2 times 1 minus x minus 1 for this one. I'm going to go ahead and simplify these, and then at that point I'm solving a system of equations like you would in Algebra 1. So here we've got y equals x plus 1, and over here we get y equals negative 2x plus 1. I skipped a little bit of the Algebra 1 steps here, but I want to focus more on the strategy on how you get this. So now what we've got is we've got these two equations. We've got an equation that models the path of object 1 and an equation that models the path of object 2. Now obviously we're using these, we're not going to be able to tell if it's a collision, but we can find an intersection. We know we're definitely going to have an intersection here because the slopes are different. If the slopes were the same, they'd either be parallel or you'd have coincident lines. So to find that point of intersection, we're going to set these two equations equal to each other. X plus 1 equals negative 2x plus 1, and we'll solve for x. And let's see here, 3x plus 1 equals 1, 3x equals 0, so x is 0. So we know that there is an intersection point when x is 0. Now we need to find the y coordinate, right? And it looks like we're actually finding the y-intercept, just happens to be where that intersection point is. That's not going to always happen. That's just sort of a coincidence here. But we want to know where the y value is. Now, if we did this correctly, then it shouldn't matter whether we plug this x in here or here. We should get the same thing. And just at least for this one example, let's test that out. Y equals 0 plus 1. Y equals negative 2 times 0 plus 1. So yeah, in both cases, we do get y equals 1. So we know there's a point of intersection. Let me scoot this up a little bit. We've got a intersection point at 0, 1, okay? But we want to know also, did they actually collide? In other words, we know this object was at the point 0, 1 at some point, no pun intended there, at some point in time. But we want to know if there's actually a collision. In other words, did they get to this point at the same time? So we need to figure that out, right? Now when we're checking this, I'm going to check all the equations here just so you can see that it's the same. Just like before, you don't have to check both x and y equations. I just want to showcase that you do get the same t value here. But so let's look at object 1. So object 1, I'm just going to rewrite this, is defined as x equals t minus 2, right? So if x is 0, we're going to plug that in there. And the y is t minus 1, so the y should be 1. And assuming we did everything right, we should get the same t value here. So t is 2, t is 2. So object 1 reached the point 0, 1 at the time t equals 2. So let's see if object 2 got to that point, that 0, 1 point at the same time. If they did, that means we have a collision. If they didn't, that just means, like the P. Terry example, that they were at this location at different times. So object 2, let's see, when was this object at x equals 0? And when was the object at y equals 1? Again, if you're solving this correctly, you shouldn't need to check both of these. You should be getting the same time. But you do need to check at least object 1 against object 2. So let's see here. What was that? 2t minus 1. So in this case, we get t equals 2. And in this case, we get t equals 2 as well. Oh, we don't get t equals 2. Wait a minute. Plus t, we get t equals 1. Oh, goodness. So object 2 got to this intersection point at 0, 1 at t equals 1, and object 2 got there at t equals 2. So object 2 got there first and was long gone by the time that object 1 got here. So we're going to say that there is actually no collision. Well, that's kind of surprising. I was kind of expecting there to be a collision. But no collision on this one. So if the question is just asking you, hey, is there a collision? Your answer here would be no. And this would be how you'd justify that answer. Let's try to do another one. So same deal here. Let's try to find whether or not we have any intersection points, and then we'll figure out whether or not they collide at the intersection point. So first, we're going to solve for both equations. We're going to solve for y in terms of x. So if x is t plus 2, that means t is x plus 2. And if x is 2 minus t, then that means that t is 2 minus x. Kind of a similar deal to the last one. Very similar problem. So then I'm going to take that x plus 2, that at 2 minus x, these t values, and I'm going to substitute them into t for the y equation. That's going to give me y equals x plus 2 minus 1 and 2 times 2 minus x minus 3. Let's go ahead and simplify those. We got some like terms. We got some distributive property. But I'm just going to kind of take care of it all in one quick step here. If you have any questions about how I get from here to here, just let me know and I'll go into a little bit more detail for you. But basically, here we go. We got two different equations for the paths of object 1 and object 2, with their y written as y in terms of x. So they definitely will have an intersection point. Both of these are linear. The slopes are different. So that guarantees at least an intersection point. So to find the intersection point, we're going to set x plus 1 equal to negative 2x plus 1. Solve this for x by adding 2x and subtracting 1. And we should get x equals 0. Is that right? Let's see. I might as well just work it out. I don't know why I'm trying to do everything in my head here. So we got, that would be 3x equals 0. Yeah, so yeah, that is 0. Okay, so we know the x is 0. Let's find the y. And it's guaranteed to work for both of these. So just to save a little bit of time here, on the last one I showed both of them working. But I'm just going to pick one. In fact, I'm going to pick the easier one. Or when I say easier, a little simpler. 0 plus 1 is just 1. So I know that I have an intersection at 0, 0, comma 1. That's not the same as a collision, though, as hopefully you've kind of picked up by now. We need to make sure that the two curves arrive at that intersection point at the same time. So for object 1, x, which is 0, we want to know at what time is the x 0, and just to double check, at what time is the y 1. Okay, I should get the same time for these. Now that I might not get the same time as the second object as we saw in the last problem, but here I get t equals 2, I get t equals 2. So object 1 hits that intersection point at t equals 2. Object 2, I want to know when that x value is 0, and I want to know when the y value is 1. So let's see when that happens. This happens at t equals 2, t equals 2. Okay, so since both objects hit this intersection point at the same time, we can say, haha, there's a collision at 0, 1. And I can say when t equals 2. All right, so this problem right here says two particles move in the xy plane for t greater than or equal to 0. The position of both particles are given below. Determine the time at which the particles collide. This problem actually came from the 1995 BC calculus exam. So there's obviously more to the question, but this is one part of it. So you can see that you're definitely going to need to know how to do this going into next year. So let's think about this. At which the particles collide. Oh, my grammar is no good. So we're going to take a very similar approach, but I'm going to show you, hopefully you've stuck in with the video here, even though we're kind of doing similar problems over and over again. But I'm going to show you a quicker way to do this. So before, on the last couple of problems, we found the intersection point, and then we went through the collision. But if all it's asking for is to determine a time at which they collide, if they even do, we don't need to go through all of that necessarily. There's an easier way we can handle this. It's a little bit less tedious. So let me kind of spell out what the steps are here. And you can actually use this on those other kind of problems too. I just wanted to kind of talk. I think this other way is a little bit more like how you would kind of think through it. But let me just throw a quick, kind of give you a quicker way to do it. So the first thing, set both x equations equal to each other. Like we want to find out what time are the x's the same. Okay, so like in this case, I get t minus 2 equals 3/2 t minus 4. In this case, we're just going to solve for t. And so we can, add 2, subtract 1.5t, and then divide. And what we should get here is t equals 4. Okay, so we know at time equals 4, their x's are the same. So again, this is just a slightly different way to approach it. For sure, the time at t equals 4, the x's are the same. So as long as the y's are the same at that time, we have a collision. Okay, we haven't actually figured out what the x is yet. Let's see, the x would be t minus 2, so 4 minus 2 would be 2. Okay, so at t equals 4, x is 2. So the second part of this process would be to plug in t into both y equations. All right, so I've got y equals t, which I'm going to use 4. Okay, so 4 minus 2 squared, and I've got y equals 3/2 times 4 minus 2. 4 minus 2 is 2, 2 squared is 4, so I get y equals 4. And that's for particle A. For particle B, I also get y equals 4. So since these are the same when time is 4, I've got my collision. So there's a collision. The two particles collide. At 2, 4 when t equals 4. So you can see it's a little less work here, okay? If you can use either method here, this one's a lot shorter for sure, but if this other method kind of made more sense to you, you're welcome to do that as well. I like to show the longer method first, just in case, because usually if you see the shorter one, you're going to stick with that no matter what. But for some people, I notice that this works a little better for them. Just kind of depends on you. So we're almost done here. What I'm going to do, the last thing here is I'm going to write out a couple of examples, and I'm not going to work through them, but I want you to practice them, and I'll throw up the answers. So give me a second to write these down, and then you work them out. All right, there you go, magic. So I've got 3 problems here, okay, where in each problem I give you a set of parametric equations for A and for B. And I'm going to ask the question, do they collide? Do the two objects collide? And if they do, tell me when they collide and where they collide. Give me the time and the XY coordinate where it happens. So take a minute, pause the video, because I'm about to throw up the spoilers to give you the answers here. So take a minute to pause the video and work these out, and then come back and hit play again. All right, hopefully you had enough time to work it out. Here we go. So the first one, you should have got 4, 3 when t equals 3. The second one, you should have got no collision. And then for the last one, you should have got 5, 4 when t equals 2. So that's pretty much it for today. So just to kind of recap, we talked about how to find the x and y intercepts of a set of parametric equations. We talked about the difference between intersections and collisions, and we learned how to find intersections and how to find collisions. Y'all have a great day, and I'll see you next time.